started a little bit later today, but we are on to Module 4, IP addressing, okay? We did a little bit of IP address stuff last year, some subnetting. We just kind of introduced the topic. Now we're going to go a little bit further in depth with what subnetting is, supernetting, all of those cool things, and how this kind of ties into our core infrastructure. Question? Yes? Yep, we are recording. So, IP addressing. So what is our goal here? To be able to set up an IP address on a workstation. But it's not just to type numbers in, right? Like we're at that level now that we are in the second year of this course where we should know what all of those numbers mean, okay? I feel like that's a line from a video game, isn't it? Like, what do the numbers mean? What video game? Mason. What do the numbers mean? Yes.
I know exactly what video game it's.
So I feel like that's what we should title this. What do the numbers mean? Because that is our goal, is to understand the different IP addresses, subnet masks, a public IP versus a private IP. These are the numbers that we are trying to find out what they mean, okay? So some of the other key terms that we'll have to know are the different type of subnet masks that we can build. My goal would be for you guys to just understand like what subnets are, why we use subnets, and then how to subnet a Class C network, okay? And I'm probably getting a lot of blank stares like, what is a Class C network? And hopefully after this module, you'll have a better understanding of that lingo, if you will. So first and foremost, an octet is an 8-bit binary number. 8-bit binary number. And then an IP address has 4 of those, okay? So, how many bits is an IPv4 address? Yeah. So, it's an octet is an 8-bit binary number, and then an IP address has 4 octets. So, what is 4 times 8? 32. Yep, it's a 32-bit number. A subnet mask is a 32-bit number that defines the network address portion of an IPv4 address. So, to simplify that, the subnet mask tells us what network we are on, okay? And we'll go through and really break down kind of how that happens, but a subnet mask identifies what network we are on. A public IP is an IP address that can be used on the internet. Converse to that, a private IP address is one that can only be used on our local LAN, okay? That is not routable on the internet. So if you see a 192.168.1.14 IP address, that is not publicly routable. As soon as it hits the gateway, it's going to be pew-pewed, so it doesn't get out onto the network. And even if it did somehow make it past the gateway, your gateway routers at your internet service provider will not forward any of that traffic. Yes? It also identifies the portion of the network address, defines the host address. So it separates it between the network and the host. That's what your subnet does, subnet mask. It defines the network portion and the host portion. And once we have some examples up on the board, we can break that down even further. Right now, we're just getting familiar with some of the key definitions, okay? APIPA. An APIPA address is your automatic private IP address. This is self-assigned. It's the 169 address, the 169.254 address. So if we reach out there and we try to get an IP address, if you remember back to last year, DORA, remember that was the steps that we go through in order to get our IP address. If for some reason we're unable to get that, you'll see a 169 address, 169.254. That is your APIPA address, an automatic privately assigned address. The next is our loopback address. Okay, the loopback is a IP address that is reserved. So in the case of IPv4, 127.0.0.1, if you type that into your web browser, it's going to loop back to itself. So if you're running let's say a Minecraft server, and you're playing it on your local machine, that's where you're going to see like that 127.0.0.1 or local host. That is also reserved to be a loopback address. Okay, so if you ping 127.0.0.1, chances are, as long as your network stack is working properly, even if you're not connected to anything, you'll still get a reply because that is our loopback. We're pinging our local network card. Next, we have our broadcast address. So anything that goes to the broadcast goes out to everybody, okay? So once we get into IP addressing and we look at like subnetting a network, you'll have to reserve a few addresses, okay? One of them is the broadcast address, the IP address that everybody gets the message, and then our network address, which is what tells us what network we're on, okay? In the case of a 192.168.0.0, that would be the network address. 0.255 would be your broadcast address, as long as we're using a standardized subnet. And again, once we actually get into seeing some of these numbers, hopefully some of this will click. And then finally, subnetting is just the process of taking a very large network and separating it into smaller sections. Okay, we're going to talk about why we want to do that. So with subnetting, there's a couple different ways to do it. Okay, there's a fixed length subnet mask. So each subnet that we make is going to have the same amount of addresses. Okay, so with that, let's say our largest group is 100 students, and we want to create a subnet for each group for each lab. Then all of them are going to be 100, whether they want it or not. Okay, a variable length subnet mask allows us to have different networks of different sizes. So let's say, here in cyber, we need access to 100 addresses, but over in welding, they only need access to maybe 4 or 5 addresses. We can change the length of our subnet mask to be more efficient, okay? It's not efficient to have all those IP addresses and not used, right? So that's the goal of VLSM, or variable length subnet masking. Not really. No, there's not really a waste of IP space. Correct. Yep. It's just a waste of space. The question was, having more IP addresses, does it slow down the network? And not really. Not really. Classless Inter-Domain Routing, or CIDR notation. It's a simple way to see what subnet masks are. So instead of saying .255.255.255.0, we would just do /24. Okay. And that's 24 bits in that subnet mask. All we're doing is counting the ones in that case. Okay? CIDR is just a way that we can notate kind of shorthand, if you will. There's a process called ANDing. So ANDing is how we determine the network address. And we'll go through and do an example of that. It's going to be a lot of math for this one, but it's very simple math. It'll be okay. Yes. So ANDing, this is all like math on paper that shows us how subnet masks work, okay? So we would have an IP address, and then below it we put our subnet mask, and the ANDing operation is when we look at the ones and see kind of what it spits out. So there's not really a practical application like what you're talking about. In this case, it's just figuring out what the computer goes through in order to figure out what's the network and what is a host, okay? Okay, so before we get into subnetting, we have to understand some of the numbering systems that are out there, okay? We're used to a base 10 system, right? Base 10 is where we count from 0 to 9, and then it restarts. And we put, a 1 in front of it until we get to the 9, and then we put a 2 in front of it. And it keeps incrementing, and we have our ones, tens, hundreds, thousands, places, okay? This is basic counting that you've been doing now for 12 plus years. Okay, this is the system that we use. So when we have, again, this is just showing you how how we build out to 6, 7, 8, 9, your hundreds, tens, thousands, and whatever. In binary, remember, thinking back to CompTIA, A+, is computers only understand zeros and ones, right? And that is on or off. So with binary, it is a base 2 system because all we know are zeros and ones, okay? So here we can make any number that we want. We're just doing it with zeros and ones. So what do we mean by that? So if I grab my pen real quick, got to find it. So with IP addresses, we have what are called our kind of our placeholder systems. So there's, in binary counting, it's, 128, and then it goes 64, it goes 32, 16, 8, 4, 2, and 1. I don't know where my fancy pants pen went. I'll just use my finger for now. So what do I mean by that? So if we take our, and I apologize if this does not show up on the video, we have our 128, our 64, 32, 16, 8, 4, 2, 1. So what we do is, using only our zeros and ones, we say what numbers are we adding to our placeholder in order to math. So let's say we wanted to come up with the number, throw a number out there. We'll figure it out together. Okay, so 256. So if we add all of these together, what does that equal? What does it equal? Do the math. Did anybody add it up? Someone bust out calculators. Who's using a calculator? We're doing math. We have a 245 as one possible answer. We have a 255.
It's 255 because it doesn't count the first bit because 0 counts as 1, right?
So if we wanted to get to 256, we would have to go over to our next place. Okay, so 255 is what we're going with there. So if you add all these numbers up together, they should equal 255, and we know it's an even or an odd number because it's going to end in 1. Okay, our last number that we're adding is a 1. So what's another number that we want to come up with? That one was a confusing one. You want to go lower, probably. Okay. So 86. Can we put 128 into 86? No. Can we put 64 into 86? Yes. Okay. So what is 86 minus 64? 22. Can 32 go into 22? Can 16 go into 22? Yes. So we subtract 16. Okay. Can 8 go into 6? Nope. And then 4, 2, 1. Okay. So this is the binary equivalent to 86. Okay. That is the basics of IP addresses. Okay. Zeros and ones, using those placeholders and being able to count up and then go the other way. Okay. That's going to be like a baseline skill that is going to help make things make sense, is doing that conversion from our base 10 system that we're used to over to binary, okay? So our zeros and ones, those are the bits. We know that. We talked about an IP address being 32 bits, right? And then where the CIDR notation comes in is when we have our binary equivalent. Actually, let me trash that. So 1, 2, 3, 4, 5, 6, 7, 8, and zeros. Okay, so we just learned if we had all ones in all the places, what number is it? It was 255, right? So we know that all ones is 255. If we count up all of these ones, there are 24 ones there. This is our CIDR notation, okay? It's simply just the number or the count of ones in our subnet mask, okay? And again, we're gonna investigate these as we go through, but I'm just trying to tie it back to that vocabulary as we go. Another one that we'll use quite a bit, this is going to be more for IP version 6, which is our hexadecimal numbering. So the easy way to break this down, hex is 6, decimal is 10, so together it's a base 16 numbering system. And the way I remember it is we go from 0 to F real quick, because now we're adding letters to our numbers and it just got super confusing, right? We go from 0 to F. That is our numbering system, and then it circles back. So hexadecimal is using letters as part of it because we go 0 through 9, and then A, B, C, D, E, and F, okay? And it gives us the ability to count a larger amount in a smaller section, okay? We can represent a larger number with less characters, okay? Binary to decimal, we kind of talked about that a little bit, but again, it's really just the skill that you need to know is this placeholder here. So when you go to take your Net Plus exam or even this exam, knowing this chart and just writing this on your scratch paper is going to help you, okay? And over the next couple weeks, we're going to have some of these problems up on the board, so that'll be kind of our warm-up activity to come in and do some of these subnetting things, because it's a really, really good skill that you need to leave here with, okay? So again, just our binary to decimal conversion, 1, not on a 64, 32, 16, all these numbers come down, and it equals 185. So again, it's that same chart that we had, the 128 to 1 for our binary conversion, and then it's going to tell us what the number is here, okay? Same thing that we just drew through on the board, same idea, okay? Hexadecimal to binary, you're not going to do as much. Use a calculator for it. I mean, in the real world, it is use a calculator. I couldn't tell you the last time I ever had to do any hexadecimal to binary conversion. I promise you that. So IPv4 addresses, getting into kind of what makes up our IP address. Here we have our different octets, okay? This is in our dotted decimal form. So we have a decimal number, dot, decimal number, dot, decimal number, dot, decimal. And then that breaks down to, if we do our conversion, we can see down here what that IP address ends up being, okay? So here is that IP address. Is it the same? It's similar. It's a 1.42. But then below here, we have this 255, 255, 255.0. This is showing us what part is our network, okay? That is our subnet mask. It's what's telling us what our network is and what our hosts are, okay? So in this case, our line stops right here because then it goes to a 0. So our network is 192.168.1 is our network, and then our hosts are in this last portion, okay? If we were to change it so it's only the first two are used in this case, 255.255, now this is our demarcation point. So our network is the 192.168 network, and then that gives us this octet and this octet to be used for hosts, which means we can have a lot more hosts there, right? Because now we have this whole area that we can use. We can't have as many networks because we borrowed from our network, but we can have a whole lot more hosts. Now, with an IP address space that has a lot of hosts, kind of tying back to your question you had earlier, yes, there will be more broadcast traffic in this type of network because it's so large that there would be a ton of traffic going across, especially when we're doing things that require broadcast communication, like that, Discover offer, the DORA for DHCP, as well as there's other protocols that use broadcast, and you'll have a lot more traffic on that network. So that's why we want to usually separate them to make them a little bit smaller so we don't have as much chatter on the network. In the Windows area, you'll see our IP address settings here, and it'll actually tell you the first one is your IP address, your next one is your subnet mask, and then you have your default gateway. Remember, your default gateway is your door out of the network. How do you leave your network? That is your default gateway, okay? So now earlier I mentioned, with a class C address, blah, 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 blah. So your standard is Class A, which is our top level. It has the most amount of IPs that are available for hosts because we're only using that first part for our network. The rest, the other 3 octets, are used for our hosts, okay? So that means we could only have, between 1 and 254 networks, and then the rest can be used for hosts. So that means we can have, 16 million? 16 million hosts on a Class A network, okay? So probably a lot of chatter happening, probably a lot of confusion and congestion on that network. A Class B means we're using the first 2 octets for our network and the second 2 for our hosts. So that'll give us 65,000 host addresses that can be used. Our Class C, which is what you'll primarily see on some of the certifications, your entry-level certifications that you'll have to subnet, are using the first 3, and the last one is used for hosts, which gives us 256 addresses. Now remember, we have to keep 1 for our network ID and then 1 for our broadcast. So that means that we have 254 addresses that'll be usable.
So what would happen if you were to set your computer's IP address to the broadcast address?
Then it would receive all the broadcast traffic. And it probably wouldn't work very well. Yeah. It would, but it would be actually it wouldn't be able to communicate or do anything. So it just wouldn't, anything that it tried to send out, it would come out from the broadcast, that it is the broadcast. Yeah. And actually Windows shouldn't let you actually set it as that. Right, set it all to everybody to the broadcast. So who passes out IPv4 addresses? So it's worth noting that we ran out of publicly facing IPv4 addresses many years ago. They were all passed out. Now it's just kind of beg, borrowing, and stealing to get your own, or they're doing some type of natting in order to share IPv4 addresses until we fully switch over to IP version 6, which we're seeing more and more, switch over to IP version 6. Which is funny because when I was taking my Cisco classes in college back in circa 2007, 2008, we were learning IPv6 back then, and they were like, oh yeah, within the next 5 years everything's going to be IP version 6. And here we are, 17 years later, and we still haven't fully moved over. But cell phones tend to be mostly IP version 6, so if you are on your phones, obviously not right now, if you're on your phones and do what's my IP, you'll actually see your IP version 6 address. So IANA is who passes out our IPv4 addresses, our publicly routable ones. And from there, they're given to our internet service provider, and then they will get those out to the end user for your modem, so that way you can connect on the internet. And even if you have 30 devices in your home, you're really only operating on the internet with your one IP address that is on your modem, okay? So it's not like each of those right now have their own IP version 4 address. Now with IP version 6, they will have their own publicly routable IP address just built into them. So they will be publicly routable out on the internets, okay? So we can see here internally, we have our 10.54.25.5. You can have, 2 machines that have the same private IP address in 2 totally different locations, okay? So if you look at, let's say Owen's house and Nick's house, they could both be on a 192.168.1 network, and they can both be 192.168.1.14, okay? Because that's their private IP address. Their public addresses are what's going to be different. And what happens is when that data or that information leaves here to go out to talk to each other, so let's say they want to have a conversation, they're going to be in their home network, they're going to go out. The IP address that is actually routable online comes over to this 72.54. We're doing what's called NAT, network address translation, to this IP address, and then they're able to send that message across the internet, okay? So looking at our IP address classes, as far as our publicly routable, we have 0 to 127 is our Class A network. That goes from 10.0.0.1 to 10.255.255. That's the private IP range that is reserved. So that means if it's before 10.0.0.1 or after 10. So basically 11. That is a publicly routable IP address. These are the ones that you're reserving for internal use. When it comes to our Class B network, that goes from 128 to 191. The reserved space is 172.16.0.0 to 172.32.255.255. Your network internally can be any of these, but you'll be assigned your publicly routable IP address from your IP, your ISP. Our Class C network is 192 to 223, and then anything that is in that 192.168 range, that is what is reserved for private use. All of the other ranges are used for publicly routable information. So if your IP address is 192.14.2.1, that's going to be a publicly routable IP address, okay, because it doesn't fall within 192.168, okay? This is a chart that I would grab a screenshot of from the presentation in Classroom, because this is some of the most common information that's going to be on your Net Plus as well as your hybrid core exam, okay? So we talked a little bit earlier about what the APIPA address is. So if you are talking to a DHCP server and you don't get an address because there's an issue with communication, you're going to be self-assigned the 169 address. Our loopback is our 127.0.1. That's what we use for our testing to make sure things are working. Our broadcast is the last IP address in the actual network itself. So for 192.168.1.0, which is most of your guys' home IP address or IP range, the broadcast is going to be the 1.255 address, okay? And that's going to be sent to all hosts on the network. Our network is the smallest or the first address in the network, and that in this case it would be the .0, because that's the first one. Bless you. Okay? It's worth noting that your gateway, it's a common misconception for people that are just starting off a network that the first usable is always the default gateway, and that's not true. Is it best practice? Is it somewhat standard that it is? Yeah, but it's not always. It doesn't have to be. So .1.1 does not have to be the default gateway, okay? It can be, but it doesn't have to be, okay? And then we're going to take a break here. And we are back. We are talking about subnets. Can someone close the door for me? So, like I said, my goal is to at least get through subnets and up to, 4.3, 4.4 today. That would be in a perfect scenario. I know it's a big module, 280 slides, so we're going to do our best. So what are the benefits of subnetting? Increased security, number one. So if you think about it, students being on the production network is probably not the safest thing in the world, right? Especially students in this class. So what we can do is we can isolate them on a totally separate subnet and create firewall rules that say they only have access to the outside world. There's no reason that a student that is on the guest network should have any access to printers, server, any of that stuff. Okay, they just get an IP address and they get out to the internet. Okay? Staff, maybe similar, right? Or they might have access to just like a copy machine, let's say. Okay, so again, by subnetting or separating our network address space, we can then keep all of our stuff secure. Yes?
Is that how there's multiple Wi-Fi networks?
Yep, and they're going into different VLANs, which are then provided different subnet IP addresses. Yep. Also, it helps for network management. So if we need to do updates to a certain area or to a certain group of computers, we can know where they're located. Also, network performance. So like I said earlier, having a bunch of hosts on one big network is going to have a, you're going to have a ton of traffic on there because people are all talking kind of over each other. It's like the commons in the morning. If you're in there, you know, a lot of people makes it kind of hard to talk. You can't just have a normal level conversation. You have to try to get just a little bit louder, okay? So when it comes to our subnetting, biggest thing that we want to get to is understanding why we subnet, which we just talked about. Talking about CIDR notation, so that way, you know, you can know the shorthand, so you don't have to write out the long IP addresses. And once you get into the Cisco side of the house, and even just like the network equipment side, CIDR notation is accepted as a way that you can input things, okay? So you can do the short form notation in the configuration settings and whatnot. So it's good to understand both, you know, and being able to go from CIDR over to, you know, your standard notation. So here's an example of our network that we are going to use. So our network ID is 192.168.5.0, okay? That means that no host can be assigned 0 because that is our network ID, okay? Below you can see our subnet mask, 255.255.255.0. That subnet mask defines the amount of hosts that we have. So in this case, we're only using that last octet for hosts. And the first 3 are used for our network, okay? So how does this actually break down? So we can see here, let me pull up my little pen, that our 192 expressed in binary is 1.1, or I'm sorry, 1.1, and then the rest is zeros, okay? And then we have our subnet mask. So in this case, we have all ones, okay? In this case, we are borrowing, you know, there's 2 that are over here, but it stops, our delineation for our network stops here, okay? So the 255.0 means that this portion right here is reserved for our network, okay? If for some reason we want to break up this network, we want to break it up into a smaller, let's say we want to break it into like 2 networks, we would then have to borrow from our neighbor, okay? So in this case, we can see where we are doing that. We're borrowing 2 bits from our host, which means this portion will now be our subnet because these ones that are down here are borrowing from our host section, okay? So we are given just 255.255.255.0 as our standard network. So if we only want 1 network, cool, that'll work. If we want more than 1, we have to borrow from our host section, okay? So let's see what that looks like. So in this case, we are borrowing 2 more additional bits, okay? So we're borrowing the 128-bit and the 64-bit. So that means our new subnet mask will be 255, 255, 255 dot, what did I say 128 plus 16 or plus 64 is? 192, okay? So that'll be our new subnet mask, and then the rest will be zeros, okay? So that's what's allowing us to borrow, or allowing us to separate this network into smaller, into 2 or multiple smaller networks, okay? We do that by borrowing from the host portion. If for some reason, if we wanted more hosts on the network, then we would go the other way, okay? We would borrow the other way. And again, because these are private addresses, we have this level of control, okay? These are not publicly routable IP addresses. This is our own private network, so that way we have full control over what is used for network, what is used for our hosts, okay? If you want to calculate the actual number of hosts per subnet, it is 2y minus 2, okay? Y is the number of bits that are available in the host ID. So if we look at our last example, we had 6 bits, okay? So 2 to the 6th power is 64. I guess you guys can't see that. So 2 to the y is equal to minus 2. Y is the number of bits that we borrowed. So, or that are left after we borrowed. So in this case, it's 6 bits that are left. So 2 to the 6th is 64 minus our 2. Why do you think we have to take those 2 out of there? What are the 2 things we need to reserve addresses for? Okay. Is it host or is it another word? Not the gateway. There are two IP addresses that we cannot assign. Network ID, and what's the other one? Broadcast ID. So that's why we're backing those 2 IP addresses out of there, okay? So 2 to the 6th is equal to 64, minus 2 is 62. So in this case, we would have 4 subnets, and each of those would have 64 usable IP addresses. Does that make sense, how we got to that number? So I would write this down. To calculate the number of hosts, it's 2y minus 2, where y is the number of bits that are available in the host ID. Okay? They are. Yep. So CIDR, like I said earlier, it's just the number of ones that are in our subnet. Okay? So let's do a quick example. What would the CIDR notation be for this if this were a 1? If those were both 1s, what is our CIDR notation for this subnet mask? What's that? So to get CIDR notation, we're counting the number of 1s that are in our subnet mask. So how many is that? It is. So we know that all of them, at each one, there's 8. So 8 times 3 is 24, plus 2 is 26. Okay? These are things that it'll come much easier once you are doing this over and over and over again. And unfortunately, that's really the best way that you can learn it, is just by going through and practicing it constantly. Okay? Which we're going to do. Don't worry. But it'll get to the point where you'll just be able to glance at this and use kind of those shorthand things. So for our class A, there is 8 1s there, so that's a /8. 8 plus 8 is what? So that's a /16. 8 plus 8 plus 8? 24. So that's our /24 in this case, okay? And that is our classless inter-domain routing. So that's just counting up the number of 1s that are in the subnet mask, okay? So our example that we had earlier, 8 plus 8 plus 8 is 24, plus these 2 equals 26 total. So the network ID here would be 192.168.5.0, and then it's a /26 network, okay? From there, we can figure out, because we know that 2y minus 2 is how we figure out the number of hosts, so that would tell us that we get 62 usable IP addresses, okay? And I'm going to show you guys a way that you can start planning out your different IP address schemes, or your IPAM, your IP address management, okay? So if you want to know the number of subnets, it's 2 to the x, and x is equal to the number of bits borrowed for subnetting. So if we have 23, that would equal 8 subnets, okay? For the number of hosts, it's that 2y minus 2, where y is the number of bits in the host ID. So in this case, 2 to the 5th is equal to 32 minus 2. That equals 30. Okay? Those are the subnetting formulas that we'll need to know. So we can see here our /16 expressed in actual 1s is 111111111.0.0. There was another period in between the first 8 ones, but you get the idea. That being said, this little chart reminds me that there are apps that do this, websites that can help you do your subnetting when you're doing this for an actual large network, where you can say, this is my IP address, I need 5 networks, go. And it'll spit it out for you. but it's important that you understand what these actual subnet means, these subnet IDs actually mean, and how they can help you when you're troubleshooting network issues. So if you're trying to ping something and it's in a totally different network, then you'll know, hey, it's probably something with my default gateway if I can't get out of my network, or there's a configuration issue, so I have to change either my IP address or my subnet mask, okay? So with our CIDR, or our full length, everything is equal, right? So in this case, we have, number of hosts, we have 2,046. Everybody has 2,000 IP addresses, okay? Whether you need it or not, you get 2,000 IP addresses. So again, that's not the best use of that address space. So that's where VLSM comes in, or variable length subnetting masks. So what we do if we're looking at our plan, we are seeing, okay, about how many hosts do all of these different departments or sections need? In this case, we're using, departments just because it's easy, accounting, management, blah, blah, blah. But a more realistic thing that you'll probably do would be like the phone VLAN. How many phones do we need in this building? Okay, that'll be our voice VLAN. About how many cameras do we need? Okay, and you want to be able to set yourself up with enough room to grow, obviously. So you go through, and then you would say, our biggest subnet is this, so that's what we're going to start with. And we are going to subnet that out. And then from there, we're going to go until we get to our smallest one. So you can see here on the right-hand side, sales has 107 hosts, accounting needs 54, human resources needs 25, management needs 5, okay? So we go through and we subnet it out, having our biggest one be the 5.0. That becomes a /25 network, so we borrow that first bit from them. So then we will get 126 addresses. So does that meet our requirements of at least 107? Yes. Now we can move on to accounting. Accounting needs 54. So in order to get an address space that has at least 54, we would go to 64, right? That is our next smallest. That is that next bit in. So the /26 network would be 64 minus the 2, one for our network, one for our broadcast. That'll give us 62 addresses. Does that meet our requirements? It does, because we need 54, and that gives us 62. Moving on to HR. HR needs 25. So our next step down is 32, right? Minus 2, one for broadcast, one for network. That'll give us 30 addresses. So therefore, it meets our requirement of 25, and then so on and so forth as we get smaller and smaller. The important thing to remember with VLSM is you start with your largest and then work your way down. Subnetting, 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 subnetting. You don't want to start with your smallest one first, because then you don't have anywhere to go. You can't borrow any more bits, right? You have to start with the biggest one and then go down from there. And it's very easy on a Class C network that this makes sense, right? It's super straightforward. But when you're starting to work with like thousands instead of ones and tens and 50s, that's when this can get kind of confusing. And in this case, we only had 4 departments, but on larger networks, especially when you're looking at like a global layout for a very large company, you have to make sure that you have all of the needed information and you set yourself up for success when it comes to expansions, okay, and reserving space for those expansions. So one of the things that we talked about on the first slide when we were talking about vocabulary is this idea of anding. So with anding, what it's doing is it's the mathematical way that if you were to look at like an app called like Wireshark, if you've ever played with Wireshark, you can actually see the bit streams that are going through, okay? So part of that is as the information is traveling on the network, it has to see what network are you a member of. And it does that with anding, okay? So with anding, what happens is, if you look on the right-hand side here, let me bring up my little pen again. This is our key, okay? So 0 times 0 is equal to 0, okay? So 0 times 0, that's going to be a 0. 1 times 0 is 0. 1 times 0 equals 0. 0 times 1 is 0, right? So what we are doing is seeing where all of our 1s end up lining up to get a result of the number 1, okay? So let's go forward 1. We can see here all of our 0s, and then we can fill it in with the other 1s. So in this case, if we add up all of these 1s together, we're figuring out what our actual IP address is, okay? So in this case, we can see this kind of natural stop where we have a large, like a bunch of zeros. That's telling us that these are our hosts, and this right here, if we add up all of our 1s, is going to equal 172.16.72.0 because of this key right here. That's all ANDing is this operation that uses this simple math where we're doing multiplication of binary numbers. I wish all math were this easy, right? So this is telling us what our network is and then what our host portion is. Does that make sense? So you line up to figure it out, let's say I just gave you, your IP address, an IP address, not your IP address, an IP address and a subnet mask. You should be able to tell me what your network ID is, okay? And you do that by lining them up right underneath each other and then doing the math straight down. And then you'll get your network ID. That's all ANDing is. Doesn't have to be scary. It's very simple math in networking. So subnetting uses. So FLSM is used in private networks. VLSM is used in public networks, but also you can do it on your own as well. There's this idea of supernetting. So supernetting, I haven't personally had any experience with or need to do anything like this. I have always just subnetted things out and we're good to go. But it is important to note that supernetting requires your IP addresses to go one after another because it's going to utilize the whole block in order to create your networks. What are the advantages? Yes?
So I assume supernetting is mostly set up by the computers themselves. So you would write a program to set each IP address one after another.
It's part of your actual plan when you're doing it. And really, the whole purpose is to have a large block in one area. So that way, when you're building out your routing tables, you have less entries because this whole block is located in this building. So you can route everything, to that area, and then it goes out to where it needs to go. So it's part of your IP address management scheme. And again, I haven't had the need to ever do any supernetting. Yeah, and honestly, as far as certifications, there's not really. I haven't ran into it very much either. It's kind of a niche thing that is covered in one slide. So, yeah, not really. What's that? I'm sure there's use cases where it is. I just haven't ran into them in my career, and other people that I've talked to and asked that question to don't have a really good. They just kind of, some of them even just look at you funny. Yeah, and it's one of those things that if you, let me do an example real quick. Like if you need it, you'll look up how to use it. So, why would you? Right. So.
I didn't mean it at all. No. You need guys on YouTube or something.
Why don't we always send me smart from well, they want to keep their USAs. That kind of makes sense.
But a lot of them actually record from India. They use the same technology there.
Okay, so supernetting. Yeah, so again, you have like that example that we were looking at with the the VLSM, so we can send all of that traffic for, let's say, North America and then Cleveland. We can send all of that to, one place. We can conserve IP addresses, because we don't have those large, numbers of thousands of IP addresses using when someone actually only needs three. Let's say they only need like 3 IP addresses. Why are we giving them 1,000? Support for larger networks, so ISPs can use them. So that is according to the world of ChatGPT. There are your advantages. So I don't think there's anything more than we haven't talked about. So perfect. So how do we get these IP addresses? So we've gone through and determined all of our different departments and our needs and the number of IP addresses. How do we get those IP addresses out to our end users? Well, first and foremost, defining what type of devices they are is important. So our servers, that fall into a certain IP range, we're probably going to go in and statically assign those, or do reservations in our DHCP server so it can pull those IP addresses. But we're going to go through and do those first. And then we are probably going to load our IP addresses into our DHCP server, so all of our different VLANs can start getting IP addresses that fall under the schema that we created, okay? So as far as what is needed for a computer to access resources on the network and out to the internet or out of their own subnet, we need these 4 things: our IP address, our subnet mask, our default gateway, and if it's going to be something that's like web-based or we're not typing in just IP addresses, we need to have our DNS server, okay? If we are using a DHCP server, these 4 things have to be loaded into the settings in order to pass those addresses out to our end users, okay? So with our DHCP scope, that is going to define the IP addresses that we had in our subnetting plan. And it's also going to have default gateway, subnet mask, and our DNS server. So a little bit of review from last year. Remember DORA. So the first thing we're going to do is discover, and then we're going to send back our offer. Then we're going to do a request, say, hey, I need an IP address, and then we are going to acknowledge and send that back, okay? So that is what our DHCP server is going to do. Now, in a traditional case of what you're used to seeing at home, you most likely have a router that does DHCP for you. It does DNS for you. It does NATing for you. It does all of the things, probably Wi-Fi, probably for you. In the case of a more business network, all of these things are done by individual servers, or one server is going to do like your DNS and DHCP, or it's going to do, you're going to have one that does DHCP, another server is going to do DNS. A router is simply a layer 3 device that allows you to access those different networks, okay? So it's not a home wireless router like you're thinking. It's actually a rack-mounted, router that has access to all these different networks or knows how to get to those other networks, okay?
They just make good business grade ones that like the same type that people use just for business.
Because you have a feature-full DHCP server in Windows Server, like it has a ton of features, and it's part of your backup plan. It's part of your resiliency plan to restore it. Instead of having all your eggs in one basket and having that one device fail, this allows you to diversify a little bit. Good question, though. They do make SOHO routers, so small office, home office type of routers. But again, I like having a totally separate device for them. Yeah.
So when we're setting up the DHCP server on that, do you want us to back it up on multiple servers?
Yeah, so we would do, you can team DHCP servers as well, so that way, for load balancing purposes, you're going to have to set up DHCP relays, and we'll explain why here in a minute. But yeah, you should do some type of backup for that in case it does go down.
We were thinking about setting up like a RAID module back there, file server, sync.
Yeah, or build, we could look at building an actual storage area network too, if it's something that we want to do. For sure. Yeah. So let's talk through the theory of and how these different things actually work. Okay, so let's build this out. Okay, so these are all different networks. Okay. This computer comes online, okay? So we just learned about broadcasts, right? Who gets the message when something is sent out on a broadcast? Everybody where? Everybody on the network, right? So this computer turns on for the first time. It doesn't have an identity really yet, so it sends out a broadcast network or a broadcast message that says, hey, where's the DHCP server, right? With the way this is set up right now, is there any way that this DHCP server would hear that message? If, these connections are not here. These are all isolated. Okay? No, right? So we need a way that when this computer comes online, that something replies and it was like, hey, I'm not the DHCP server, but this is where the DHCP server is, okay? So it's really important to understand that that first broadcast message is that first step in getting an IP address. So when you are receiving an APIPA address, when you get a 169 address, you need to start troubleshooting, okay, how is this message not getting out from my localized network, and what do I need to do to get that traffic to be seen by that DHCP server, okay? So what you're going to do in this case is you have what's called an IP helper address. And what happens is in your actual router, which is, again, it is part of this network, you have a DHCP forwarder or an IP helper. As far as Cisco is concerned, it is the IP helper address. So you can see the configuration here that on interfaced fast Ethernet 0/1, we put in our IP helper dash address and we type in the IP address of our DHCP server. So what happens then is, with this being our multiple networks, this is the .1 network, this is the .2 network, this is the .3 network, this is the .4 network, this is the .5 network. When this traffic leaves here, it is tagged with the number 1. So when it finally makes it to our DHCP server and it comes in, it says, hey, I came from the .1 VLAN, okay? So the DHCP server has different scopes based on the layout of the network. So it's like, hey, you came from this .1 VLAN, you're going to get an IP address from the .1 scope, okay? That's what allows it to all actually function and not have to put a DHCP server in each of these different networks, okay? We forward that traffic to the DHCP server and it's tagged by what VLAN it came out of, so that way the DHCP server knows, hey, you're supposed to get an IP address from this scope. Yes?
Is it possible to trick it into forwarding you into a separate network?
Yes.
from the DHCP server?
Yes. Look up double tagging is what you're looking for. Erase. So what you'll do is you'll go through in 4.1.11 and you'll have to configure some IP addresses. So let's get through 4.2 and then we will take a break for the day and then circle back after lunch. So what are some of the things that we need to be able to identify when it comes to either getting an APIPA address or not having connectivity? Okay, the first one is that APIPA, right? The automatic private IP address. That means we can't talk to our DHCP server. DNS, are we not getting a proper DNS server? Do we not have access to that DNS server? What happens if we ping the DNS server? Do we get a reply back? Things like that. And then it could be a rogue DHCP server, right? Because it is broadcast, which means anybody on the actual network can say, hey, I'm the DHCP server, let's start talking, and then it'll reply back, okay? So the way that we go through and troubleshoot is having a good idea or a good understanding of what right is supposed to look like. Not this right, a different right altogether, okay? What does the right network look like? What are the proper subnets? What are the proper subnet masks, okay? How is our network actually laid out? This is why documentation and diagramming is so important, okay? When you first take over a network, especially if it's like a hostile takeover and the person that they get rid of didn't want to leave, you know, you're going to have to pretty much do a lot of discovery and figure a lot of this out on your own, okay? So when we're troubleshooting, making sure that your network is properly set up, that your subnet mask, you know, nobody fat-fingered it, going through and verifying your documentation is the best way to go through and make sure. If you're not getting outside of your network, that means your default gateway is probably set incorrectly or you can't access the default gateway from your local network, okay? So what I've always done is kind of figure it out step by step. Okay, locally, you know, do I have, you know, connectivity on my local LAN? Yes. Okay, can I ping the next hop? Yes, I can go to the default gateway. Okay, hop onto that device. So let's say it's a router. Can I ping that router's next hop? If I can, okay, let me go to the next one. And it's just one at a time. You're going through methodically figuring out where your issue lies, okay? Going through and verifying your DNS connectivity. Is the DNS server up? Can you ping the IP address of the DNS server? Log into that DNS server. Is the DNS service running? Is it actually, allowed to or able to take any queries to its phone book? If so, start doing that whole testing the next one up because it is going to operate as the DNS server for everybody below it, but it gets responses from upstream, okay? From the internet servers, maybe it's Google, maybe it's, Cloudflare. One of those, it's going to get its updates from there. So can it reach its DNS server? Can it go out of its default gateway to get updates? Okay? Methodically, go step by step, hop by hop to verify where your issues lie. Okay? Yes?
So say you were to buy a router and install it in your house. Would the default DNS server depend on who the internet service provider is?
Yeah, I mean, they'll have their own DNS server or the configuration that they push out to those routers is going to be like a Cloudflare or a Google. Like at Nova, I think we push out Google as ours. 8.8.8.8, yeah. Two, usually two. I think on Linux you can do more, but Windows, say again? I'm pretty sure it's two on Windows. Like a primary to backup is what it's always been. And internally, we used to have, you would do like a primary domain controller and a backup domain controller, and those acted as your DNS for the network, and then they updated from the ones in the sky out in the ethers. Yeah. So we can see here, if for some reason our DHCP server went down, we would then get assigned APIPA addresses. Now, technically, you could still talk on this network with everybody getting APIPA addresses, right? But if there was like a static IP set for our file server, well, obviously we wouldn't be able to talk to that because it's not on the 169.254 network. But there was a time there when IoT devices were kind of new And that's actually what they did to configure them, is you would set yourself to their network, which didn't have a DHCP server, and it had a static IP in the 169 address space, and then it would wait for yours to time out. You would self-assign an IP address, and then you would be on the same network, which is a pretty cool way. I mean, it's a cool idea. Not really how it's supposed to be meant to be used, but that is possible, yeah.
Can you assign a static 169.254 address?
I don't know, it should error out, but I don't know if it does. But that would be super confusing. Would be super, super confusing. How do we fix that? Do an ipconfig/release and then an ipconfig/renew, or do a release renew. Check your DHCP scopes, check that IP helper command, make sure it's forwarding to the right server. Those are some common things that you can troubleshoot. So there are quite a few labs that have troubleshooting in this because it is super important that you understand, how to go through and do the simple things like ping and release renew to the more difficult things like verifying what network you're in. So we will pick up with 4.3 after lunch. Does anybody have any questions? All right, so picking up where we left off with 4.3, troubleshooting IP communication. So today we're going to talk about some of the tools that we use to figure out where we're losing our traffic or where our problem lies. Some of the terms you need to know are ping. So that's an ICMP request that goes out, and it's almost like echolocation from a dolphin, right? So it sends out these signals and then waits to hear what it gets back. And then we have our address resolution protocol, which sounds like a seal in ARP, but it's actually a protocol that ties the MAC address. So if we're looking for IP communication, we're going to use ping, and then the underlying protocol that works on layer 2 is going to be the ARP protocol. So when you're first running into an issue, so let's say the servers in the classroom are not reaching out or not getting a connection to the internet, okay? So these are a couple questions that we would want to ask ourselves. We would want to say, is the issue happening to many systems? So we have 5 servers plugged in and none of them are getting out to the internet, or is only one of them affected? Is it an entire department that doesn't have access to a server, or is it only one user that can't get to the website? Okay, so first is understanding really the scope of the issue, so that way you can start to troubleshoot in just that area. If you don't go through and narrow that down, then you are going to have, it's going to be too wide, and you're not going to be able to break down exactly what the issue is. So in our example here, the internet host is unreachable, okay? So we can see our 2 devices here, and our third one does not access the internet. So our topology has a router. That's the one there that has the arrows all pointing either direction. Then we have a firewall. We have the ISP, or our internet service provider, and then it goes out to the internet. So our user sends in a help desk ticket, says I can't use the internet. We go to their computer and we first try to reproduce the problem, okay? We could also do a kind of a reverse engineering way that we can go to our help desk and we can see what devices, what the MAC address is of that device if we have it notated anywhere, and look at our MAC address table and see what IP address it was signed if we can't physically get there. So we could try to figure it out through the internet and then send them a ping request. So we're going to go ahead and ping the server. So in this case, it's 74.125.195.102. Note that it has this -6 in there, okay? So this is going to send, that's I think was one of the questions on the GIM kit, but sending more of those packets. So you can see there, ping 6, ping -6, and then see, what is happening. Are we getting information back, or is nothing happening, okay? On the Windows side, it'll only send 4 of those ICMP requests. On Linux, it'll just keep going, okay? Which is nice because if you're working in a data center and you're trying to get connectivity back, you can start the ping for the server, and then as soon as you plug it in, you'll actually start seeing ping requests show up on your laptop. Okay, so that's what's nice. You can make that happen in Windows as well. I want to say it's like ping-r. Somebody look that up. That will actually be the command that'll keep it. It'll keep sending ping requests. It won't stop after 4. So what could it be? So in this case, it could be the firewall is blocking ping requests like we have here in the school. If we try to ping an IP address, that instantly gets nuked, right? With those ping requests automatically fail because we block that ICMP traffic. It could be misconfigured IP information, right? Either on the server side or the client side. But with other clients able to access it, it's more likely the client side issue. It could be that, how can we fix or how can we troubleshoot this? How can we really find out the scope of the problem? We can try different websites, right? So we, tested just that one server, but we probably should test a couple other ones as well. And then finally, we can ping other hosts that are on the internet, okay? So once we know that, okay, we don't have access to that website, we kind of work our way backwards, okay? So there's 2 different ways that you could troubleshoot this. You can start here and ping to this interface on the router. You could ping then to this interface on the router. You could ping to this interface on the firewall. You can ping to this interface on the firewall. We could then ping to this part of the ISP, and then to this part of the ISP, and then out to our server IP. Okay, it's worth noting that these are all different steps along the way, okay? These are all part of our journey to Mordor. We want to check them individually. We don't just check, out to the internet and say it doesn't work. We have to figure out where traffic is being lost, okay? Yes?
So if you were unsure how many different access points were between you and the internet service provider, would you just use like a tracer?
Yep, you'd use trace route and then see your different jumps along the way. Which when you do a trace route, it's kind of telling you like where it works because it's showing you the path. So you know that you can get to there, and then all of a sudden, once you try to make a hop, it'll just die. So the trace route will also help you do that kind of along the way. Yes. GGs. Good questions. Pew, 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 pew. Another thing too, just making sure you have good network connectivity and that like your network connection is working. You could also ping just another client on that actual network. So when we want to see our IP information on a Windows machine, we would type in ipconfig/all, and that will show us our IP address, our default gateway, our DNS information. It'll tell us whether it's DHCP or static. Okay, so if you look at it and it's static, it kind of makes you go, maybe this static IP address is being used somewhere else on the network, so that's why we're having some issues. Again, ipconfig is where you'll want to start, and being able to understand that ipconfig is what we talked about previously. Being able to look at this ipconfig, seeing the subnet, and knowing what network it is in, it's supposed to be in, that can help you quickly troubleshoot as well. Okay. Who knows what that command is on the Linux side? Anybody? ifconfig and then what? Any idea? So there's several different commands that you could use. ifconfig is the old standby. In newer versions of like Ubuntu and whatnot, that is deprecated, so you have to actually install that application in order for it to work. Yes. Yes, the other one would be the ipconfig. So it'll just be the word or the letters IP, and then there's several different switches as well. Okay. So we could see here that we have IP address that was given to us from our DHCP server, but what do we know about that IP address? What do we know? What's weird about that IP address that we were given? Everybody should know this one. I know that you know it.
I can't see very well, but it looks like an APIPA address.
It is an APIPA address, and what does that mean? Yes.
There's not a DHCP server that contact, so it's not getting an IP address from it, it's not automatically assigning itself one.
Correct. So when we go through that DORA process of trying to get an IP address, at some point there was a failure, so that's why it was given that 169 address. Okay? Do we understand that? Okay, because that will show up on an exam. So in summary, using ping, that kind of helps you test along the way to make sure you can make it on your path. IPconfig is a great tool that will help you understand kind of where your problem lies. So in this section, we're going to talk about DHCP. I'm going to set up a DHCP server, but then we have to talk about how we use a DHCP server when we have multiple different subnets, okay? So some of the key terms for this section, IP range. So this is like addresses for, like, let's say there's some houses in a subdevelopment. They all have different addresses in a group. Subnet mask is telling us what network they're in, okay? We talked about this a lot last week. IP exclusions, so you might be using a static IP and you don't want the DHCP server to hand that IP address out to anybody, so you can exclude that IP from the range. IP reservations are, before something shows up, you can get the MAC address and go into your DHCP server and say, hey, I want this copier to have this IP address. And then as soon as you plug it in, the DHCP server will be like, hey, here you go. Here's that cool IP address. Lease time is how long you have your IP address for. What would be a reason that you want to have a lease time? Yes? Okay. So do you think we should have long lease times or short lease times? Okay. Okay. Yep. Sure, yeah. Traditionally. But you can set it to whatever you want. So the question that I posed is it better to have a long lease time or a short lease time? We only have a finite number of IP addresses to hand out in our subnet, right? So when we were looking at subnets last week, we talked about 250 some addresses. Well, think about the school district here with every student. Okay, when there was a student when there was a student Wi-Fi network, okay? There was 500 students, each of you have at least one device. So if we did a lease that you had it for 8 days, then we're gonna have to use up a lot of IP addresses, right? But if we had a lease time of 8 minutes, that'd be a ton of broadcast traffic, right? Because it's gonna go through that process and re-up, and it just adds more congestion on the network. So finding that balance based on your actual environment is going to be key. Yes? Would the optimal lease time for the building be around 6 hours? Sure, yeah. I would probably do it 8 hours, but yeah. Yep, just outside that day. So DHCP, so what DHCP allows us to do is to assign IP addresses with a server that does basically documentation for us. So I once worked at a school district around here that did all static IP addresses, and they kept track of everything in a spreadsheet, okay? That was wild to me. It worked for them, but that was just wild to me because it's just, I can't even explain why that's a great idea, because it's not, but it is possible. So your DHCP server is what is responsible for handing out IP addresses throughout your network. So something comes online, it goes through and does its discover, offer, request, acknowledge, and then your computer will get your IP address, the subnet mask, and the default gateway at the bare minimum. It'll also most likely get your DNS address as well. Okay, so that way, if you do type in, google.com, it actually knows what to do with that information. Okay. So our scope of our IP addresses that live within our DHCP server tells us what our IP configuration is. So step one, let's say we're doing a new network here at the building. We're going to go pen and paper first and figure out what the needs are for each area. Are we going to have a different subnet per program? Do we just need to section off some programs because they need to be isolated or they're heavy users like us? Do we need to, are we going to use that for throttling, or does something need a higher quality of service? So we determine our needs first, and then from there, we would go through and subnet it with our little fancy, subnetting formulas that we learned last week, and then we would type that into our DHCP server, okay? So we're gonna have our scopes for all our different subnets, any options that it needs as far as where's the imaging server, where's the DHCP, or where's the DNS server, things like that. Okay? Yes?
Why does the graphics lab have their Wi-Fi?
Because they also require more bandwidth than most. Yep.
Yeah, don't they use like mostly Adobe products over there?
Yep. They do a lot of cloud type of things that require.
Their internet seemed a lot more responsive when I was in their
They were the exact same.
It seemed more responsive.
Yeah, they have the
Might have
same.
been Mac versus Chromebook.
Could be. Yeah, that'd be a difference. Also, I mean, if your Chromebook was probably on the student network then, where theirs was on the actual network, which has more bandwidth. So yes, you saw live a reason why you would subnet something, to give it more access to bandwidth. So we can see here we have our IP range goes from 50 to 100. Our subnet mask is 255.0, 255, 255, 255.0. We have exclusions of 50 through 55. Okay, so we want to go through and say we're going to keep these first 5 available for in case we need to troubleshoot something or we need to assign a static IP address. We then have our reservations. So we want, this device, this -64 device, to get IP address 56. So that way it always has the same address. Another thing that is important for, especially with copy machines, because you might replace a copy machine. So when the new one comes in, you just go in there and swap out the IP address. So then you already have the IP address as part of the print function. So then you just have to go update the driver on the actual print server. So it makes it really easy to upgrade all your clients, say 1,000 clients, to be able to print to a new copy machine. We then have our lease time. So in this case, it's 4 days and 12 hours. We have what our default gateway is. What's another name for the default gateway? Like, what is its purpose? Slade, what's the purpose of the default gateway? Yep, that's where we leave our network and come back into our network, right? Just like leaving the country to go to Canada. Okay, that is our default gateway. Then we have our DNS server, which is our domain name service. Yes. Yes, 8.8.8.8 is, and they might also be 8.8.4.4. 1.1. Yep, Cloudflare is 1.1.1.1. Okay. No idea. So this is that DORA process that we learned a little bit about last year. We have the first one, which is the discover packet is sent out. We then have our DHCP server sending an offer back. Then the request comes in from the client that says, hey, I need an IP address. And the server will then send back that acknowledgement, okay? When we're doing a renewal, we have the request and then the acknowledge. So it's just doing the RA part because it already knows the DHCP server. Yes?
So when it receives the DHCP request, does it just read it, or is there any way that you can bypass that?
In what way? Why would you? Okay, so the question is when the request comes in, is there any way to bypass that?
Maybe not bypass per se, but could you put malicious information in your DHCP request to stick on the server?
No, because it's just saying, all that request says is, where is the DHCP server? So that attack that you're looking to do would be a rogue DHCP server that then is doing DNS poisoning because you're sending that client a DNS server that you've poisoned. So when they go to, say, gmail.com, it redirects to your version of google.com, so then you could do credential harvesting there. Is that what you were going down that about? Yep. Yep, so that's why it's important to have protocols set up that stop, rogue DHCP servers from being on the network. So you basically determine like what your trusted ones are, and then this DHCP server will actually look for, do DHCP snooping to see if somebody else responds, and then you'll get alerts. And you could actually do this at the, I believe the switch level, the router level. You can actually set it up to send alerts, so that way, as that traffic's coming through, it'll see it and then ping you. Yes. So another thing that's part of DHCP is one of your options is your imaging server, okay? So imaging meaning how we deploy, say, Windows or different operating systems to our machines. There's two things that are put in there. The first option is the actual server in which it's going to boot to. And the second part is what image it's going to pull down to be able to boot over the network, okay? So there's a really cool attack that I've wanted to do for a couple years now that utilizes that, where you could actually get it to boot to your own version of Linux, whether that's Kali, Parrot, whatever it is, because a lot of times when you're locking down or hardening a end user system, you block booting from USB, right? That's an easy thing to do. But you still need to manage that device. So a lot of times the PXE booting or the network boot option is still set to the first one. So if we could somehow like have a Raspberry Pi, let's say, that's running in lightweight imaging server, so you just plug it into the back of the network cable, it then boots to Kali, is that an attack surface that we can maybe start to explore? So that's something that I wanted to look at this year for what that looks like, because you're literally going to have a box that you just plug into the network port and then potentially have it boot into your environment. Yes? Chromebooks don't boot from the network. They boot from the cloud. Yep. Yep. So yep, we talked about DHCP's role and all that fun stuff. So a relay. Sometimes, okay, so I want you to take a step back and think about what we talked about when we were talking about subnets, right? At the end of the day, what do subnets do? What is their purpose? Yes. They divide networks into different broadcast domains, right? Correct? Yes. Fail. So we separate networks into different broadcast domains. So knowing what we know about DHCP servers, we have that first step in the DHCP server, and what is it? Yeah, discover. And what type of traffic is discover? Yes. Okay. It is broadcast, right? So subnets break up our broadcast domains. So if we have a server, okay, we're going to have network 1, we're going to have network 2, we're going to have network 3, right? So in theory, in order for clients that are connected to this network, so we'll build a client real quick. In order for this client to get a DHCP, an IP address from a DHCP server, it's going to send out a broadcast request, right? And then we're going to have a server right here that's also plugged in that's going to be able to go through the process. Dora, right? So then if we have a client that's over here and it's plugged into this network, what would we have to have on this network? Yes. Okay. Or if we didn't know anything about relays, what would we have to have plugged in here? Yeah? You would need to have another DHCP server, right? And then if we have a client over here that needs an IP address, what would we have to add to this server? What would we have to add here if we didn't know about relays? A DHCP server, okay? So what we do then, let me erase that real quick. Instead of making all of these different DHCP servers, what we do is we create what's called a DHCP relay, okay? So theoretically, all of these are coming into our router, and then they're going out to the internet, okay? So in this router, we do what's called a IP helper address. So then what happens is this broadcast traffic comes out, and then this router says, basically it does the offer part. So it's going to offer it, but it's going to say the IP address of this server. Because then what happens is it switches to a unicast transaction. So the unicast transaction can then go through our router interface. So these are our default gateways, right? Default gateways are designed to kill broadcast traffic, okay? Your default gateway will kill broadcast traffic. Broadcast traffic cannot leave the actual network, or it'll just start looping around and it'll kill everything, okay? So we don't let it happen. So that broadcast traffic from this device will be converted over to unicast. So then once it gets to this interface right here, it can then safely go through and have a conversation with our DHCP server, okay? So that is the idea of our IP or our relay or our IP helper, okay? The IP helper is a network device that performs the same actions as a DHCP relay agent for UDP-based protocols, such as network time protocol. So the IP helper will help that traffic get from one network over to the other one, utilizing, taking in that broadcast and then switching it over, okay? So this is just a fancy way to show you how all that works. Yep, our DHCP offer comes through. It says, hey, this is how you get there, and it gets it across the network. I like my diagram better. All right, so we are going to take a break there at 4.6. Go ahead and work on the labs, and there's like, 6 or 7 labs, I think, in Module 4. So I just want to give you guys time to stay up to date, so that way if you have questions, I can answer them before we move forward. All right. We ended up with, last time we talked about the DHCP relay agents. So now we are going into some of the more advanced topics when it comes in through DHCP. Okay, so at the face value, DHCP helps us get an IP address, but it's probably one of the most important servers that exist on the network, right? Just getting us that IP address so that way we can connect out to the outside world. So we should probably start looking at some things like failover and different ways that we can make sure that this server stays activated, okay? So number one, we're going to talk about configuring our failover, and then we're going to talk about setting up additional scopes, and then we are going to make a split scope, okay? So you're probably wondering, what in the heck are those things? So we're going to talk about them. Some of the vocabulary that we need to know for this module. First one is DHCP failover. Anytime you hear that term failover, it means there is something there in case something fails. It's like a backup, right? If you look at Major League Baseball teams or NFL, they have a backup quarterback or a backup pitcher, right? That is their failover. If something happens, they have some type of backup plan. So in the case of DHCP, that just means there are 2 servers that share a pool of IP addresses within the scope, and then both servers have access to all addresses, right? Because it's not enough that, actually I want you to think through this. Think about, we have 2 DHCP servers, okay? We have just a backup one. Let's say the first one goes down, and then the second one's like, okay, I'm ready to take over. If we just have a fresh DHCP server and spin it up, what kind of problems do you think would happen? Why is it important that they have access to all addresses in the pool? Yes?
They didn't, the second one would know which IP address is which.
Yeah, so if a second server comes online and it doesn't know what IP addresses have already been leased out to computers, it's going to start leasing them again, and now we're going to have 2 houses with the same address, right? And we try to send mail, and we're not going to know where to send it to, and we're going to introduce a bunch of issues within our network. Because remember, our DHCP leases have a certain time in which they expire, and that's when they renew those leases. So if it's, say, a 5-day lease, which I hope it's not, and a server goes down, what's that? 8 days? Yeah, 8 days or 8 hours? 8 days. So in that case, if they most likely have failover set up, But if it's not going to check in with that DHCP server for like 8 days, okay? So hot standby. We've talked about this before when we've talked about different levels of our ability to come back after, whether that's a cyber attack or different standby procedures, our redundancy procedures. A hot standby is basically when a DHCP server is just going to kind of hang out and just kind of watch how things happen, and then it takes over when that other server goes down. If we're in load balance mode, using terms that we know, load balance meaning we're trying to go, we have this really heavy load and we're trying to make sure each arm carries about the same amount. That's the same thing when it comes to DHCP, right? We have both DHCP servers will share that scope, and they'll, as requests come in, they'll be like, oh, you take this one, I'll take that one, so on and so forth. So they each have about equal, right? The other thing that we need to know is our maximum client lead time. This is the maximum amount of time that the backup server will wait before taking over, okay? So with, brief outages and stuff like that, it's going to hang out and be like, well, I don't know, like, are you down? Are you down? And then it'll hit that timer, and then it'll be like, okay, it's my turn to take over, and kind of runs with the mission from there. But it's not going to instantly take over when there's like a blip of an outage on the network. It's going to sit and wait until it has that maximum amount of time that we have determined, okay? And then finally, we have our DHCP filtering. That's how we're using our client MAC address to determine if our machines that are actually requesting DHCP addresses, whether or not they're actually supposed to get one, okay? So if we start seeing your personal devices on the cyber network, we can go on there, we can right click and say, don't give an address, and then next time you connect, it's going to look at its thing and it's be like, you're not on the list, or you are on the list of people not to give an IP address to, and you won't receive that IP address, okay? So looking here, we have, just talking about splitting the DHCP scope. When we do this, we want to make sure that it's that 50-50 split, right? We don't want one server to be overrun. We want to try to find that balance. And this sounds super, super complicated, but I promise it's not. Windows does a really, really good job of doing all of this autonomously, okay? There's also another term here that we might not know. That is cluster, okay? So here in the classroom, all of our virtualized servers are in a cluster. So if we need to move them from one server to another, we simply click a button and it does a live migration over to the other server. Okay, that's because they're all clustered together. When you cluster something, you take all of the resources and kind of pool them together, and then you can allocate where you need them. Okay, so Windows has really good failover built in order to automate a lot of these tasks. Okay. DHCP failure started back in 2012, so it's already been over 12 years since we had this just baked in. Okay, before we would kind of have scripts and stuff that would monitor if services went down, and then we would fire up that backup server if need be. Okay, DHCP server, like I said, also helps with load balancing and redundancy, and then sharing that scope, right? Because it has to keep notes of where we left off when we were handing out our IP addresses. Like I mentioned earlier, it's very, very easy to do this, okay? So when you go into the labs, you'll go through and do your configuration. You simply go through into the configure failover, tell it which scopes we're going to use. We're going to hit next through this, and it's going to do all of the configuration for you. It's going to create the scopes. It's going to set up the communication between the two servers, so that way we can make sure that we have redundancy with our DHCP servers. So by the time it's done, you can see here that we have our load balancing where they each have about 50% of the workload on that network, okay? So now, if one of them goes down, it can look at its notes and be like, oh, I know which scope, the rest of the scope, I can throw that into mine, and we can work off of just one DHCP server for the time being. And what's nice about this is we can have this forward information across different sites, okay? it doesn't necessarily all have to be on one physical location. We can set these trusts up across town if they have network communication. Okay? So with our hot standby, it's just basically waiting until that goes down, and then it'll just power on. With load balance, it's constantly. Okay? You start with load balancing mode from the beginning. Hot standby is kind of a backup, like, hey, are you down, are you down, are you down? I'm going to take the ball and run. Whereas our load balance is, it's always on, right? Both of the VMs that have that DHCP role are constantly leasing out addresses and stuff like that, okay? So, again, load balancing starts from the beginning, taking requests and sending out IP addresses. Hot standby is meant to sit and wait until something goes down, okay? DHCP filtering comes in when we have our clients that maybe we've marked as being, bad actors on our network. And we would go through and say, we're not giving you any information. Or we might assign you a bad address that's not going to route anywhere, okay? So with that, it helps with keeping the network secure and also making sure that right from the rip that we're not passing out IP addresses to the bad guys. Now, can the bad guys still just set a static IP? Absolutely, right? We can't really necessarily stop them from doing that. But, we could do our best for the script kiddies, if you will, okay? So for this lab, you have 2 DHCP failovers that you guys are going to work on, and then you're going to configure 2 different scopes, a regular scope and a split scope, right, between the 2 machines, okay? And then we will pick up later at 4.7. Any questions? Labs there. So let's talk a little bit about troubleshooting, okay? So what do we do when we see a 169.254 address? What is that? What is that?
That's an APIPA address.
That isn't a APIPA. And what does that mean? Tristan.
Something's wrong with the DHCP server.
Right. It's set to automatically request a DHCP to send out that broadcast, that discover packet, and nobody responds. So it has to self-assign. So that's really our red herring when we are troubleshooting stuff to look at our IP configuration. What's the command that we type in the command line to see our IP address? ipconfig/all. Yes. Question.
So if their network adapter isn't working, so they can't reach out to a bigger network, would it still assign to a 169 address?
Yep. If it's set to DHCP, that's what it's going to do. Yep. So DHCP, there's something wrong, so we will try to send out that request. We don't get any response, so it will go through and it will self-assign on that actual network. So you can see here 169.254.0.2, and then there's also 0.1. Like I said, there was a time when the home automation stuff, they came default in the 169.254 subnet. So that way when you connected to their Wi-Fi, you wouldn't get an IP address, so then you got an IP address that was on the network, right? Because it was getting a 169 address. So it was an interesting way for them to do it. Yes?
So with the APIPA addresses, if there's multiple on a network,
Uh-huh.
would they be able to see that and get one that isn't already being used?
Yeah. Yep, that's what they're showing here, where it's like that self-assigning and it's incrementing. Yep. IP version 6. It's so difficult. There's letters with numbers. So in this section, we're going to talk a little bit about DHCP 6 and how those IP addresses are handed out. When we actually break down a IP version 6 address, we have a couple different areas, okay? So the first thing is the prefix ID, and that's the first 64 bits of the address, and this is going to be broken down by the United States, and then from there, the ISP, and then from the ISP, they probably break it down even more, okay? So the first part of an IPv6 is really to identify basically where it's physically located. The last 64 bits of the address is your unique identifier for each device. So this is very similar to a MAC address, Okay, it actually takes the MAC address as part of the calculation in order to do that. Okay. Tunneling is what we do when we are taking, like, us at the ISP level, like we are running IPv6, but we're not running IPv6 out to clients. They're still on IPv4. So in order to have this network kind of interface, we have to either NAT those addresses. So when they get to us, there is a like port-based or some type of natting that's going on that says, when you leave here, you're getting this address, and then when you come back, we're giving you the IP4 address. Okay, so it's this kind of this 6 to 4 NAT that's going on, but you can also tunnel that information. So in that case, it would have an IP version 6 tunnel, and your IP version 4 traffic is inside. Our unicast address, so this is a one-to-one, uni meaning one. So this allows our hosts to talk to one another. A multicast address is when we have a group of computers. So where you traditionally see multicast is when you're doing things like imaging, okay? And basically the commands or the data is just sent out to the group as a whole, and then this group is like sitting here waiting to receive it, okay? And it makes it so you can image a lot faster instead of having a one-to-one conversation. Like right now, what I'm doing is I have you guys in a group, right? And I am sending this message out, and hopefully you're all receiving it, okay? That's more efficient than me going one-on-one and doing this entire conversation over and over and over again, one at a time. Yes?
So is multicast another version of UDP?
No, I mean, a lot of times it will use UDP in order to do that transmission, but this actually has to do with the IP addresses and what they're assigned. There's actually a reserved section for multicast addresses. After 255, I believe. I would have to double check. It's an automated thing. So, right. Anycast is basically where you can have two hosts that share an IP address. So with that, you see it more for like standby stuff where, you know, one is going to die and then one comes back up. I've never had to use an Anycast address, but it's just a newer feature set in the IPv6 world. I am by no means an IPv6 expert. I'm still using IP4 for everything until I'm forced to use IP version 6.
Wasn't there a big security problem with IPv6 with Windows in the past month?
Probably.
I know.
We'll have to look it up.
ISP you have, but they can directly access your computer without hitting the router first.
Yeah, so with IP version 6, we were scared to run out of IP addresses, right? So we designed a system where we would have thousands per capita. Like, it's a wild amount that you can have, like, per square foot of your house. Like, it's a ton. The idea is everybody has their own unique address based on their MAC address that you don't have to have, say, a router, right? You can just talk to the open internet. Now, obviously, you're going to need a router to get to a modem, and we still need to route traffic around, but you don't necessarily have to wait for a DHCP server to give you an IP address and do all that stuff. You have your own idea or your own identity that you can then talk on the internet. So it makes sense that they would have access to that because, you know, you're using IP version 6 and everybody has a direct to the internet IP address. You're not going back through your router and doing that. Yes?
Before it gets through the modem, does it change your IPv6 address at all?
In a perfect world, no. Like, you'll have your own IP version 6 address, and it's just basically passing that on over the modem. Right now, we're using our routers as NAT devices, so we are NATing, doing translate, right, because we're sharing an address. We're sharing one public IP for our entire house. Or in the case of the school, we have like 10 public IPs that are shared with all the schools. So as the internet, as the internet traffic leaves here and goes to TCCSA and then out to the world, they're assigned an IP address out of the pool. Like, they're pooling all of the NATable addresses together. Yep. But in a perfect world, like, we would all have our own IP version 6 addresses here in order to communicate on the World Wide Web.
But wouldn't that also mean that it's slightly more vulnerable?
That's what happened on Windows. People were able to
Yeah.
directly access.
I mean, you would still have the traffic is still going through a firewall, right? Like, there's still a path in which traffic goes through security devices. And also you have your local firewalls too, that can be set up to block those things. So yeah, I mean, there's good and bad with both. You can see here is what a 128-bit address looks like with that first 64 like we talked about. So there is approximately 340 undecillion addresses. Undecillion, I guess. That's a lot. What's really cool is, it's really easy to remember IP version 4 addresses, right? I mean, they just kind of roll off the tip of the tongue. With IP version 6 addresses, not so much, but you can simplify them, okay? So do you see how there's a bunch of zeros in this? You can go through and remove those leading zeros down to just the 2 colons, as long as it is all zeros, okay? Also, you'll notice that, these zeros are at the end. We already did our leading zeros in the front, so we wouldn't be able to do it there. Just like the zeros that we have like at the 0F56. We're not able to necessarily do those, like condense them down. You could just physically remove them, and the protocol is smart enough to see that there should be a colon there. Like it can unpack that address, okay? And we can look at this bottom address and figure out, where the zeros go back in, right? We can use our powers of deduction, like on Scooby-Doo, and figure out how to, re-expand them. Here is our, showing where it has that prefix like we talked about. This is going to be the more regional area on the left-hand side, and then our interface ID based on the MAC address is on the right side. The first one is the site prefix. You can see here, that's going to define the location. And then the last section there is the subnet ID. So this is breaking it down into more organized. Like this could be the north section of our coverage area. This could be the west section. This could be the central section. It just helps us to organize things a little bit better. And then the last part is our MAC address, where it's the unique identifier. Okay, so this is showing how they flip the bit. Not something that is super important for you to know, but it is showing how they take the MAC address and they turn it into the actual interface ID. Okay, it's called flipping the bit. You make one bit a 1 instead of a 0, and then it expands it out. It does all this crazy stuff. But even for like my CCNA, I did not have to know how to do that. It's not super important. Just note that that interface ID is based on the MAC address, okay? Dual stack configuration, this is when we're sending both our IP version 4 and our IP version 6 traffic. It's, again, there's a lot of protocols that are in place to help us transition over to IP version 6, because when I was in college back in like 2009, 2008, like they were talking about how IP version 6 was going to change the world, and within 2 years we were going to all be switched over to it. Spoiler alert, we're not. The only people that have done a really great job, or the only industry that's done a great job with this so far, has been the cell phone companies. So once they've kind of worked it out how it works, now once the DoD does it, then we'll probably see more mass adoption. But if that's not high on the DoD priority list, then manufacturers really aren't pushing for this to happen. You know what I mean? Yeah, so like I said, the cell phone companies are all doing a pretty good job with it. What's that? Yeah, it could be. You could slowly see IP or ISPs starting to, hand those out. Tunneling, we're just putting a packet inside of another. Teredo tunneling. So basically, we're just, again, taking that IP version 4 network, and we are tunneling it into the IP version 6 network. Same thing here, 4 to 6. We're encapsulating it and shooting it over. These are all just different ways that we are putting things in place in order to someday, hopefully, switch over to IP version 6. We also have our link local. So again, if we break down these words that we might not know, link means connection, right? Local is on our network, everybody that we could talk to like in this room. And that is where we can assign a IP address, IP version 6 address, to have just our local communication. And we can talk to one another and negotiate what our addresses are going to be. We can talk to each other on our network without having to have, say, a DHCP server. So this is a very autonomous thing that can sometimes give you a false sense of connection because you're like, I could talk to my other computer, like it's pinging and whatever, but I'm not getting outside the network. Well, it's because you're using your link local address to talk to just somebody else on the same network. Okay, it's just like you guys can talk to each other and communicate, right? Because you're in the same room, and I haven't given you an identity, right? You either self-assigned or you have your own identity. You came into the network with that, like you can then communicate, right? So it's the same thing. It can discover its neighbors. It can set up its own automatic address. Okay. Again, our multicast is set up for groups. Loopback is the all zeros with a 1 at the end. That's our loopback address. So if we need to test the networking stack to make sure the network adapter works and whatnot, we need to ping our own network card. That's the loopback address that you would use on IP version 6. Okay. All right. Going through and talking a little bit about IPAM, or IP address management, okay? So with this, we're basically figuring out and managing our resource when it comes to IP addresses, okay? So we're allocating how many addresses do we need per subnet. We're optimizing IP address use, so we're not going to take a subnet that has 5,000 IP addresses when we only need 100, let's say. We want to make sure that we are adding our support for DNS and DHCP, making sure that users get those IP addresses that they need, but also that human-readable URL or their domain name that they can use to communicate on the actual network itself. For this, we're going to use the latest and greatest when it comes from Windows, and we're going to set up our Active Directory, so that way we all have user accounts. And then from there, we can go through and set up our policies in 2 ways. We can either do manual provisioning, where we're going through and figuring out, hey, you're going to get this IP address because I said so, or we can set up group policy, where we build a standard of what perfect looks like and then allow the computer to kind of make that happen, okay? When it comes to storing this information, Windows has their own kind of internal databases that we don't interface with, so there's no way for us to get access to that data other than what they provide for us. But then there's also the availability of the Microsoft SQL Server. So with the Microsoft SQL Server, we can actually write queries against it and do more, generate more reports and stuff like that. So a little bit more flexibility, but you would have to pay for a license for that, okay? So when we're actually looking at our IP space, we want to take into consideration, again, the quantity of IP addresses that are going to be needed. Do you think we estimate that for now, or do we want to estimate that over multiple years when we're first setting up IPAM?
First setting it up?
Yeah.
I would say it matters what type of company you're in, but I would say for smaller companies, you would want to do it for what it is right now.
Okay. Because you don't want to basically spend more or do more work than you'd have to, right?
For bigger companies, if you have a high turnover rate or just lots of people joining in, you would want to keep it higher.
Right, and you want to forecast for, a certain amount of growth based on historical data, right? So, like we've seen a growth in student population here over the last couple of years, so we want to make sure that when we're setting up our student network that the Chrome devices use, we want to make sure we're taking that into consideration, right? We want to make sure that we have enough IP addresses for that. NIC teaming, so this is where we're going to use our network interface card. They're going to work together, and you're able to, instead of having just say 1 gigabyte port, we now have 2 that are teamed together that can provide more bandwidth, which is nice, especially when you're using, software like Proxmox or Hyper-V. We're going to be moving a lot of data through that interface card, so it's best to kind of team them together in order to get the most throughput as possible, right? We want to make sure that we have, our customers have a good experience when they are utilizing the services that we're offering on servers. So why do we do NIC teaming? Obviously for load balancing. So, as things are getting busier, we can hand them off to a different network card if we need to. Also fault tolerance. So if one dies, we instantly have that hot spare that's there. And what's really cool is up to 32 NICs can be teamed together. I've never seen a device like a server that had 32 network interface cards, but it's good to know that those things can exist, okay? So again, with fault tolerance, they're all sharing that same IP interface, that 10005. So if something dies, then they still have access to the actual network, okay? LACP, the Link Aggregation Control Protocol, which is LACP, that is where we're actually setting up that aggregation, bringing those network cards together in order to communicate over that interface. The lag, there. I don't think we need to go into the actual hashing of how it works. That's more than we need to know. So with dynamic mode, we can actually change on the fly. That's what dynamic means, right? So with that, it's going to hash the address in order to see if there's like spikes in any traffic that's going to a certain interface, and it'll use that hash to do the the failover or the load balancing.